Molar volume. Molar mass was the mass of 1 mole. Molar volume is the volume of 1 mole. But here we're talking about gases. And Avogadro, this is the same Avogadro who came up with Avogadro's number. Avogadro's law is his observations based on his experiments with gases. His observation was that 2 gases containing equal numbers of molecules occupy equal volumes under similar conditions. What this means is if you have 1 mole of hydrogen and 1 mole of oxygen in 2 separate containers, same set of conditions, they're going to have the same volume. This is a thing about gases that's very different. This is not true for liquids and solids, because the size of the particles matters. In a gas, there is so much empty space that the size of the particles doesn't matter. And so it's the number of particles that's important. So if you have the same number of particles, you'll have the same volume under the same conditions. Now, the volume of a gas is definitely affected by temperature and pressure. And so we need to specify these things. And when you get to 1A, you'll get into a lot more detail about the gases. For now, we're just going to look at what's called STP, standard temperature and pressure. Standard temperature is 0 degrees Celsius. This is the freezing point of water. This is a temperature that's easy to obtain. These experiments were done back in at least the 1700s. They didn't have electricity. They didn't have refrigerators. They didn't have, electronically controlled thermostats and stuff. So if you take a big ice water bath and put your container in there, you can know what the temperature is. It's going to be 0 degrees Celsius, because that's the temperature of ice water. So if that helps you remember, we need to remember what standard temperature is. Standard pressure is 1 atmosphere. This is atmospheric pressure at sea level. So again, very easy to obtain. If the pressure on the inside of this container is the same as outside, you pretty much have 1 atmosphere of pressure. So that's standard temperature and pressure. And you're going to see STP a lot in this section, and that means at standard temperature and pressure. So molar volume is the volume of 1 mole of any gas at STP, and it is equal to 22.4 liters. It doesn't matter what the gas is. At STP, 1 mole of any gas occupies 22.4 liters. I meant to bring down, we actually have a wooden box upstairs that's 22.4 liters in volume. I meant to bring that down, but along with my calculator, I forgot. But this illustration will help give you an idea of how big that is. So this is a cube that occupies a volume of 22.4 liters compared to a standard-sized basketball. So 1 mole of gas at STP is a reasonable volume. It's not ginormous. So this is important, this guy right here. 1 mole equals 22.4 liters at STP. You should memorize that. Yep. 22.4. So this table from your book is sort of illustrating the relationships here. Here we're comparing several different gases: hydrogen, oxygen, carbon dioxide, ammonia, and argon. Argon is an element, and its gas contains atoms instead of molecules. We're looking at 1 mole of each of these. They have the same number of molecules, or for argon, it's atoms. Avogadro's number of particles. Because they have the same number of particles, they have the same molar volume. 1 mole will be 22.4 liters for all of them. Are their masses the same? No, the masses are different. The mass of hydrogen is much less than the mass of argon. So the masses are different, but the volume occupied depends only on the number of particles, and so that is the same. So we can use that 22.4 liters is equal to 1 mole as a conversion factor. So 1 mole of a gas at STP equals 22.4 liters. So calculate the volume of 13.6 moles of helium gas at STP. They're giving us moles. They're asking us for volume. So let's use liters. It doesn't say we have to do any particular one, but liters will be convenient. This is the only relationship we need. So 13.6 moles times, there's one arrow, there's one conversion factor. Liters on the top, moles on the bottom to cancel out. 1 mole occupies 22.4 liters. We don't have to remember, should I multiply, should I divide? The units tell you what to do. So 13.6 times 22.4. Both of these numbers have 3 significant figures. I'm going to round my answer off because my calculator is showing me 304.64. And I want to keep 3, so I'm going to round this off to 305 liters. Any questions? Yes?
22.4, is that exact?
It is not exact. It is not. Good question. Anybody else? How about this one? How many moles of argon are in 25.0 milliliters of the gas at STP? What unit are they giving us? Milliliters. And the unit they're asking us for? Moles. Yeah, we're going to have to go to liters in between. This relationship is between moles and liters, not moles and milliliters. A decimal point isn't very good, is it? That's better. This volume was given in milliliters, so first we need to convert to liters, and then we can use the molar volume to find the number of moles. So 25.0 milliliters. This time I've got 2 arrows, I've got 2 conversion factors, unit factors. Our path is milliliters to liters to moles, so we've got milliliters to liters to moles. And then we take this unit, and that comes into the denominator. And then liters comes down here. All the units work out. Units first, then numbers. You can do this one first or that one first. So maybe this one seems a little easier because it's written right up here. 1 mole, 22.4 liters. 1 mole, 22.4 liters. This is a metric unit conversion. Here we have milli in the bottom. What does milli mean? 10 to the negative third. So I'm not going to put what it means with its abbreviation. I'm going to put what it means on the other side of the line. 10 to the minus third. Which is the same as 1 times 10 to the minus third, and that's easier to enter into your calculator. So you've got 25 times 1 EE minus 3. 25 times 1 EE minus 3 divided by 22.4. And this is a small number. I'm going to put it in scientific notation. This is equal to, I'm going to round this to 3 sig figs, 1.12 times 10 to the minus 3. And the unit is mole. Any questions? Gases are much less dense than liquids or solids. And we usually express the density of a liquid or a solid in grams per milliliter or grams per cubic centimeter. And we can express the density of gases in those units, but they end up being really small numbers, much smaller than 1. So typically we use the unit grams per liter instead because it gives us nicer numbers. we can actually calculate the density of a gas at STP. And to do that, we need to remember what density is. And so this is a relationship that you should remember from earlier in the semester. Density is the mass divided by the volume. For gases, we're going to be looking at the mass in grams divided by the volume in liters. Let's calculate the density of hydrogen sulfide gas, H2S, at STP. The molar volume of all gases at STP is the same. The density is not. The volumes are the same, but the masses are different. So to calculate density, and again, I'm going to do this slightly differently than your book presents it. If the book way makes more sense to you, go ahead and do it. But I'm gonna do what I feel comfortable with and what seems to work for a lot of students. They're saying calculate the density. So I would say, okay, what is density? Well, density is mass over volume. So that will be grams, and because this is a gas, we want liters in the denominator. So I need to find the mass of this gas and the volume of this gas. They gave me no numbers in this problem. What do we do? We're going to use the periodic table. We have the formula for the gas. Using the formula, what could we calculate from the periodic table? The molar mass, right? The mass of 1 mole. So 2 times the mass of hydrogen plus the mass of sulfur, 2 times 1.008 plus 32.07. Oh, it's a bad day for me in calculators. 34.086. Grams is equal to 1 mole. So that's something. I would round that to 4 sig figs, so I'm going to underline that. I'm not going to round it now because I don't want to round my numbers till the very end to avoid rounding errors. But I just underline the 8 to remind myself that number only has 4 sig figs. Okay, so there's a mass. That's the mass of 1 mole. Could we figure out the volume of 1 mole? Yeah, what's the volume of 1 mole of gas at STP? 22.4. So we know that 22.4 liters is equal to 1 mole. Basically what we're doing is we can just choose the amount of gas that we're talking about. Density is a property that does not change with amount. It's called an intrinsic property. The mass of something changes if you have more or less of it. The density of something does not change. So we can just choose the sample size. So we've approached it this way, but you could also say, well, let's just say I have 1 mole of this. Let me find the mass, let me find the volume, and then I'll divide them. You could choose 5 moles or 72 moles or something else, but 1 is a lot easier. So then I'm going to take these numbers and I'm going to put them into this equation for density. The mass of 1 mole of it is 34.086 grams, and the volume of 1 mole at STP is 22.4 liters. 34.086 divided by 22.4. And now I'm going to round. I'm actually going to round this to 3 significant figures because of 22.4. 1.52, and the units are grams per liter. And that is a very reasonable gas density. Any questions? So a problem like this, when you first look at it, it may not be obvious what you're supposed to do. Much of life is like that. We don't just get handed lists of do this, do this, do this, and life will be great, right? You kind of have to figure things out as you go along. Chemistry problems are like that. So you look at it and you think about it and you say, well, density, what is density? STP, oh, what do I know about that? And you just start writing down things that you know, and hopefully then you'll be able to figure out what you're supposed to do. So you're going to have to puzzle at some of these a little bit, and that's okay. It's good for you. It increases your brain power. Let's do another example. Boron trifluoride gas is used in the manufacture of computer chips. Okay, that's one of those little fluffy sentences. Kind of interesting, not necessary to the problem. Given that 1.505 grams of the gas occupies 497 milliliters at STP, what is the molar mass of boron trifluoride gas? This isn't asking us for the density, is it? What are they asking for? Molar mass. Okay, so let's write down what we're given, because that's always a good place to start. We've got 1.505 grams, and we have 497 milliliters, and this is at STP. And they're asking us for the molar mass. What's molar mass? It's the number of grams in 1 mole, right? So it would be the mass in grams divided by moles. Molar mass, mass per mole. So if I know the mass and the number of moles, I could divide them and find the molar mass. Do I know the mass of this gas? Yeah. So 1.505 grams. Do I know how many moles there are? Did they give it to me? No, they didn't. Did they give me some information that I could find the number of moles? Yeah, they gave me the volume. The volume of a gas at STP. Molar volume of a gas, 1 mole equals 22.4 liters. So what I need to do is I need to take my milliliters and go to liters and then go to moles. We did one that was just this part earlier. Now we're doing this to get the number so that we can stick it in there. So 497 milliliters, 2 arrows, 2 conversion factors. Milliliters to liters to moles. Put the milliliters down here so the units cancel out. Put liters down here so the units cancel out. 1 mole is 22.4 liters of a gas. It's one of the things that makes gases easy to work with, is it's very easy to figure out how many moles there are. They're pesky to work with because you have to keep them in closed containers, otherwise they tend to go away, right? You know, water doesn't do that. You put it in a beaker and it'll stay around. Eventually it'll all evaporate, but that'll take quite a long time. If you had a beaker of gas, within a couple minutes it's basically gone. So that makes gases difficult. But just by looking at their volume, we can figure out how many moles. So that makes gases awesome. Milliliter. So milli on the bottom, what it means on the top, 10 to the minus third. 497 times 1 EE minus 3 divided by 22.4. And this is what my calculator says, 0, or what Josh's calculator says, 221875 moles. How many significant figures should that answer have? 3. So remember, these leading zeros don't count. So 2, 2, and the 1. I'm going to underline that. Yeah, that's number of moles. Oh, brain hiccup there. So I want to put that up here. And I'm going to take 1.505 grams and divide by 0.0221875 equals, and this comes out to be 67. How many significant figures should that answer have? 3. This one is limited to 3 because of this starting number. So this is going to be 67.7, and the units are grams per mole. Is that a reasonable molar mass? You have a question? Well, from its name, we could figure out the formula. But if they didn't give you the formula, from this information, the mass and the volume that it occupies, you can calculate the molar mass. And there are some situations where you need to do things like that. But you're right, you could do boron trifluoride is BF3, and you could just calculate it from the periodic table. Is this a reasonable molar mass? What if I came up with 0.5? 0.5 grams per mole. Is that a reasonable molar mass? Is it possible for any compound to have a molar mass of 0.5? No. What's the smallest element? Hydrogen, 1.008. And even that exists as a diatomic element, so it's a molecule of 2.016. Anything smaller than that, you did something wrong, right? And we shouldn't end up with numbers that are, like 5,000 or something for a gas. So any questions about that problem?